Hello there. This is Dr. Benson with another exciting statistics lecture for you. And today you are going to be learning about correlation. And correlation is a really important thing to understand because there's limitations involved with correlation. So correlation does not equal causation. A lot of this lecture will be devoted to that. And because correlation is probably the most common type of statistical analysis in social science research. So a lot of research is based on correlational studies and correlational analysis. So it's important for you to be able to interpret what a correlation coefficient tells you and to understand that just because two things are correlated doesn't necessarily mean that one thing causes another. So let's kind of do a recap of where we've been and now where we're going, because correlation is very different from the types of analyses that you've been exposed to so far this semester. So thus far, we've been examining whether an independent variable has an impact on a dependent variable by examining the difference between a sample mean and a population mean. So remember when we did z-tests and t-tests for single samples, we looked at the difference between a sample mean and a population mean. And our hope was that the independent variable that we manipulated in our sample changed our sample so that their mean was different from the population mean and they no longer represented the population. It was highly unlikely that we would get that sample mean due to chance. So we suspected that we got that sample mean because the independent variable had an effect on the dependent variable. Then we took that kind of methodology a step further with the t-test for related samples and the t-test for independent measures and ANOVA. So for the t-test for related samples, the most common way would be to do repeated measures, right? So we would say, okay, we're going to measure this sample, then we're going to manipulate the independent variable, then we're going to measure the dependent variable in the sample after we manipulate the independent variable. And if there's a difference in means for the dependent variable before and after the manipulation of the independent variable, and that difference is not likely to occur due to chance, right? That difference is greater than the standard error. That's all what test statistics is all about, right? Comparing the observed difference to the difference expected just due to chance. Then we would say we think that mean difference occurred because the independent variable had an effect on the dependent variable. Then with the t-test independent measures, we had two different groups, two different samples, who each received a different level of the independent variable. And then if the difference between their means exceeded the difference we would expect to see just due to chance, or the standard error, we said there was a significant difference and that we would expect, again, whenever we say there's significant difference, we would expect to see a similar situation in the population. We think that the independent variable had an effect on the dependent variable. We would expect to see that in the population as well. Then with ANOVA, that's basically like an independent measures t-test with more than two groups, and we would compare the differences between groups to the differences within groups in hopes that the differences between groups, right, the differences that are also due to the independent variable exceeded the differences within groups, the differences just due to error, and we could think that, oh yeah, the independent variable had an effect on the dependent variable, and we would expect to see a similar thing that we saw in our sample in the population. Then we did the two-factor analysis of variance, where we had two different independent variables with multiple levels, and we looked to see if those two independent variables had main effects or interaction effects on our dependent variable, and so we could make conclusions about differences there as well. So the differences in ANOVA, in ANOVA, t-tests, and z-tests, the differences in the dependent variable are based on either the manipulation of the independent variable or by grouping individuals based on their pre-existing level of the independent variable, right? If we had a quasi-independent variable like age, we could group people by age, but we didn't manipulate that. Well, I basically just gave you a summary of the entire semester in a couple of minutes. Hopefully I didn't overwhelm you. Just trying to give you some context of where we've been. So now, instead of focusing on examining the differences in the dependent variable between groups or samples differentiated based on the independent variable, we are going to focus on examining the relationship between two variables measured in the same sample or group. So we're only looking at a single group, and we're looking at two variables measured within that group. So the independent variable and dependent variable are not always explicit in these situations. We don't always know what is the IV and the DV, but when they are, and when we have some assumptions about which variable out of the two that we're looking at is the independent variable and which variable is the dependent variable, we'll label the independent variable as X and the dependent variable as Y. So when we were looking at scores before, right, we had just x values. Well, now we're going to have x and y values. We're measuring two different variables for every person in our data set. So again, we may not know which variable is the independent variable and which is the dependent variable. We're mainly just examining whether or not the two variables are related. And the word related in this context just means that there's a consistent pattern among scores on the two variables such that higher or lower scores on variable x are consistently related to higher or lower scores on variable y for each participant in our study. So I'm going to cover the three characteristics of relationships, so form, direction, and strength. Then I'll get into the 4 steps of a hypothesis test with correlation. Those 4 steps are the same as they've always been. We're still going to state the hypothesis, find the critical value, only now the critical value is for correlation. Then in step 3, calculate the test statistic, the correlation in this case. And then in step 4, see if what we calculated in step 3 falls in the critical region set by step 2, and then make our decision and state our conclusion based on that, right? So if what we calculated falls in the critical region, or the rejection region as I like to call it, we reject the null. If the value we calculated does not fall in the critical region or the rejection region, then we fail to reject the null. And we don't have a significant correlation. Sad times. Okay, then part of this lecture will cover why correlation does not equal causation, why you should be cautious when people are trying to say that something causes something else when the data is just based on correlation. So the first characteristic of relationship is form. So what shape do data points form for all study participants when you plot x and y into a scatter plot? So a scatter plot is different than the types of graphs we've seen in the past. So before, we were plotting the values along the x-axis, be they sample means or scores, and then the frequency of those values along the y-axis or the vertical axis. That's no longer the case for correlation. We are plotting the value for x and the value for y for each study participant. So the value for x goes along the x-axis, the value for y goes along the y-axis, and we're going to have dots in our graph. And each dot represents one person's score on x and y. And you'll see plenty of examples in this lecture. So when you plot your data in a scatter plot and you see scattered, right? Dots are just all over the place. There's no relationship between variables. So it looks like a shotgun blast, right? You plot your data and it's just crazy scattered. When there's a relationship among variables, though, the data points will follow either a linear pattern or a curvilinear pattern. And those are two different forms of relationships. So you can either have a linear or a curvilinear pattern, or no relationship, it's just scattered all over the place. So when you have a linear pattern, the points in the scatter plot come close to a straight diagonal line. When you have a curvilinear form in your data, then the points in the scatter plot form a curved line, usually like a U or an upside down U. Well, the correlation coefficient that I will be discussing today is the Pearson correlation coefficient. So you see that listed right here. And the symbol for that is R. Now, the Pearson correlation coefficient is a single numerical value that describes the strength and direction of the linear relationship between two variables. So I'm going to talk about strength and direction here in a little bit, but for now, just know that the only type of correlation that we are going to be working with is the Pearson correlation, and the Pearson correlation is only appropriate for linear form data. So if you have a curvilinear relationship, Pearson's R is not appropriate, the Pearson correlation coefficient. Also called Pearson's R because the symbol is an R. Also, Pearson's R is only appropriate when you have two variables on a ratio or interval scale of measurement. Now there's other correlation coefficients for nonlinear data or data that's nominal or ordinal. That information is available in the textbook. I encourage you to look into it. It is really interesting to know that there's different types of correlations, like the Spearman correlation when you have curvilinear data. But I'm not going to cover that in this lecture. It's beyond the scope of this class. This is an introductory level statistics class, so I'm only going to cover the most basic and most common type of correlation, which is the Pearson R correlation. So here's some scatter plot humor for you. So These will make a little more sense once you learn exactly what a scatter plot is, but there you go. Here we have a nonlinear pattern, right? We've got like a U shape happening here, and it makes me really happy. And then here, it's always important to label your axes. So if you're actually drawing scatter plots on your own, you need to label what is the variable for x and what are the values, and then what is the variable y called and what are the values. I would totally break up with somebody for not labeling their axes, but that's just me. Okay. I got to step up the humor. I got to keep up with Dr. Marshall here. All right, so here's an example of a curvilinear relationship. And just to kind of point out how a scatter plot is constructed, each row in this table represents one person, and we're measuring stressful work events in the past quarter, seeing if there's a relationship with their performance appraisal score. So we're calling stressful work events variable x because we think that stressful work events is what's predicting the performance appraisal score. We think that is the independent variable and this is the dependent variable. However, we're just basically measuring these all at the same time. We're not manipulating anything. So maybe if you have better performance, then you are experiencing less stress, or maybe if you're experiencing less stress, you have better performance. We don't know which one comes first. But we're assuming that stressful work events is the independent variable based on past theory and research. So we're labeling that X. Okay, so again, each row represents one employee. This one had 0 stressful work events in the past quarter and a 50 on their performance appraisal score. And the dot in the scatter plot for that person, we would go to 0 for X, 50 for Y, dot. Right? So this represents this person. The second person had a 5 stressful work events in the past quarter and got a 70 on the performance appraisal. So you would find 5 along the x-axis, go up to 70 along the y-axis, and boom, there's your dot. Now, this is made up data, but it's based on past research that suggests that when you have really low levels of stress or really high levels of stress, you have worse performance than when you have moderate levels of stress. So if you think about it, if you have really low levels of stress, maybe there's just no motivation to do any work. Nobody's breathing down your neck. There's no hard deadlines. You're just kind of slacking off and nobody cares. You're not even stressed about it. Your performance bottoms out. Whereas if you're on the high end of this spectrum and you're just got work overload, the boss is always breathing down your neck, you've got too much to do, you're so overwhelmed, your performance will also be lower. But theoretically, and based on past research, if you have a moderate level of stress, you have just enough stress to keep you motivated, but not so much that you're overwhelmed, then your performance is at its peak. So this is a curvilinear relationship. There's not a consistent increase or decrease in Y as X increases. It switches gears. So it's kind of a curvilinear form. You would not want to analyze this data with Pearson's correlation coefficient or with R because it's not a linear relationship. So that's an inverse U curvilinear form. Here is a U-shaped curvilinear form. And this is identifying the relationship between age and car insurance premiums. So when you're really young, you're really high risk, right? Your car insurance premium is higher. You're young. You don't really care. You think you're invincible. You haven't been driving very long. You're more prone to make mistakes and have accidents. Then as you get really old, you start to kind of lose your senses a little bit. Your vision gets worse. Your memory is less accurate. You can't hear as well. And hell, maybe you're just older and you don't really care if you get in a car accident because you're on death's door anyway, so who cares if you die? That's horrible, but maybe that's part of it. I don't know. All right, so then, just like the last example, we had this like sweet spot in the middle, right? Well, here we've got a sweet spot in the middle where car insurance premiums are really low when you're just old enough to care and be experienced, but not so old that you're reckless or that you can't see or hear very well. So another curvilinear relationship. It's not a consistent increase or decrease in Y. As X increases, it changes, right? So it starts off getting low. So as X increases, Y decreases. And then all of a sudden, as X increases, Y increases. Curvilinear, not appropriate for the Pearson correlation coefficient. Now let's look at some linear relationships that are appropriate for Pearson's correlation coefficient, or R, what we're going to be looking at. So here's an example of time studying in hours and quiz grades. So we're calling time studying in hours X because we think that X is predicting quiz grades, or Y, right? So we think this is our dependent variable, quiz grades, and that time studying hours is our independent variable. But we're not 100% sure, although in this case it's pretty clear, right? Okay, so as x increases, you see a consistent change in y, right? Y is consistently increasing, so we have a linear relationship here. When you plot the data, they tend to form a straight line. Linear, right? We don't have a point where all of a sudden the pattern switches. Now, this is also a strong positive relationship, but we'll talk about strength and direction here in a little bit. Now we have another linear relationship between hours of cardio per week and percent body fat. We're calling hours of cardio per week X because we think that is what's predicting body fat, right? We think cardio is our independent variable and body fat is our dependent variable. So we also have a linear relationship here. As X increases, we have a consistent decrease in Y. When you plot the data visually, we see a linear form, right? It's fitting a straight line. This is a strong negative relationship, but we'll talk about strength and direction. Now, let's talk about direction. Okay, so the direction of a relationship tells you how the variables are related based on whether scores on the low or high end of one variable's range correspond to the low or the high end on the other variable's range. And for our purposes, when we look at the correlation coefficient, the sign of the correlation coefficient, is it positive or negative, tells us the direction of the relationship. So if x and y tend to change in the same direction, so in our data, if those who have higher scores for x tend to have higher scores for y, or those who have lower scores for x tend to have lower scores for y, then the relationship is said to be positive, right? The two variables are changing in the same direction across participants. So we would have a positive correlation coefficient. If the relationship is positive, the value is positive. So some examples of this: food intake and weight. Those who eat more tend to weigh more. Those who eat less tend to weigh less. Study time and quiz hours. Those who study more tend to get higher grades on the quiz. Those who study less tend to get lower grades on the quiz. Those are positive relationships. Then negative relationships. So if x and y tend to change in opposite directions, so if those who have a higher score on x tend to have a lower score on y, or those who have a lower score on x tend to have a higher score on y, then this relationship is negative. And when you look at the correlation coefficient, there will be a negative sign in front of the value for the correlation. So some examples of negative relationships: cardio exercise and weight. Those who exercise, well, let's talk about percentage of body fat, because weight can be, muscle mass as well. So cardio exercise and percentage of body fat. Those who do more cardio tend to have less body fat. Those who do less cardio tend to have more body fat, right? Opposite direction. Negative relationship. Now let's look at class absences and quiz grades. Those who miss more class, have more class absences, tend to have lower quiz grades. Those who have fewer class absences tend to have higher quiz grades. It's an opposite change, right? Higher X, lower Y, we have a negative relationship. So let's visualize a positive relationship. So that quiz grades and time studying in hours example. Not only if we look at the numeric values in our data, we can see as x increases, y tends to increase as well. But when you plot it out, you see an upward slope. So if you're driving a car on your scatter plot, you're going uphill. So if you're asked to identify the direction of your relationship and explain how you know based on the form in your scatter plot, you could say, for this one, I have a positive relationship because when I plot my data in a scatter plot, it has an upward slope. So as x increases, y increases as well. And you can see that the value for the correlation coefficient is a positive value, positive relationship. Negative relationship. So as we can see here, as x increases, y tends to decrease. And when you plot this in a scatter plot, you see a downward slope. So if you're driving a car on your scatter plot, you're going downhill. So you can also see that the value for this correlation has a negative sign in front of it. So I'll show you how to calculate Pearson's correlation later, but for now, just know if it has a negative sign, you have a negative relationship. They're changing in opposite directions. If it has a positive sign, you have a positive relationship. X and Y are tending to change in the same direction. So if you were asked to predict the strength of this, the direction of this relationship based on the scatter plot and explain why you think this is the way it is, you would say, I think this is a negative relationship. I think it has a negative direction because when I plot my data in a scatter plot, it has a downward slope. Higher scores for X tend to correspond to lower values for Y, or more exercise tends to correspond to less body fat. So strength is the last characteristic of a relationship that I want to talk about for correlation. And this strength tells you how consistent the relationship is among variables. And strength is denoted by the numeric value of the correlation coefficient. So direction is based on the sign of the correlation. Strength is based on the numeric value. And the numeric value for correlation only ranges from 0 to 1. You're never going to have a correlation coefficient that's like 1.5 or negative 1.5. Again, the correlation coefficient only ranges from the absolute value of 0 to 1. And I say absolute value because you can have negative values, right? You're just never going to have a correlation coefficient with an absolute value that exceeds 1. Remember, absolute value just kind of ignores negative numbers. So a strong relationship is a situation where every time x increases by 1 point, Y, when you look at your data, Y is changing by a consistent amount across all study participants. So for example, if you had a perfect relationship, you had a 1 relationship, right? Because 0 represents, remember here, less consistent relationship, weaker. 1 represents more consistent relationship. If you have a correlation coefficient of 1, you have a perfect relationship, and maybe you have a situation where each additional hour of study time consistently yields 5 more quiz points. Or each additional class absent consistently yields 5 less quiz points. So that's a situation where every time x increases by 1 point, y changes by the exact amount. That would be a perfect relationship. Then a weak relationship would be every time x increases by 1 point, y changes by a variable amount across all study participants. There's no consistency there. So maybe for each additional hour of study time, it would yield a small point increase for some on the quiz, a large point increase for others, and maybe even a point decrease for some. So if you plotted that relationship in a scatter plot, it would be all over the place. And when you calculated the correlation coefficient, it would be a really small value. So it's important that you understand that strength and direction are two separate things. So the direction tells you, do my x and y tend to change in the same direction or opposite directions? If they tend to change in the same direction, each person has an increase in x, tends to have an increase in y, then you would have positive. If it's opposite direction, you have a negative relationship. That is separate from the strength. Don't think that just because you have a negative correlation that it's weak, or just because you have a positive correlation that it's strong. For strength, you're simply looking at the numeric value, regardless of if it's positive or negative, right? That's why we have this absolute value here. So be careful with that. So, as you see down here, you've seen R squared before when we were looking at the t-tests. That's a measure of effect size. Well, the cool thing about correlation is you can literally square the correlation coefficient for Pearson's R and you get R squared. So these two things are very closely related. So when we look at the evaluation of correlation strength, it's closely tied to the evaluation of effect size. So remember, for R squared around 0.01, we said that was a small effect size. Well, if we take this 0.01 and we square root it, we end up with 0.10. So 0.01 square root, and you get the correlation. Because the square root of R squared gives you R, just like the squared version of R gives you R squared. So if you have a small effect size, then you can say that you have a weak relationship. Just showing you how these numbers are related. So when you're evaluating correlation, if it's around a 0.10, absolute value, right? It could be negative 0.10 or regular old positive 0.10. You'd call that a weak relationship. If it's around 0.30, moderate relationship. Around 0.50, strong relationship. And anything 0.70 and above is very strong. Now, if you had a situation where you calculated your correlation coefficient and you had a 0.40, it's like right smack dab in the middle of these two, you could say moderate to strong relationship, cover all your bases, and you're good to go. Now, when you visualize the correlation, you can also tell if the relationship is strong or weak. So if your data points fit a straight line perfectly, right? Perfect linear relationship, then that tells you you have an extremely strong relationship. If you see a situation that looks like this, where even if you look at your data, right, so it's perfect linear, this would tell me my correlation is a 1, not a negative 1, but a positive 1, right, upward direction. And you can see that for each 500 calorie increase, weight is increasing by 50 pounds consistently across the board. Now, I showed you this example because it illustrates what a perfect linear relationship looks like, something that would have a correlation of 1. But guess what? You almost never see data that looks like this in research, so don't buy it if a researcher tells you they have a perfect relationship. It's probably not the case. There's always variation happening. But here's a situation where, again, for every 500 calorie increase, weight increases by 50 points consistently. Plotted out, perfect linear relationship. You would have a correlation of 1 because not only is it a perfect linear relationship, the strongest it can get, but it's positive, upward direction. As x increases, y increases. Here's a situation where we have moderate strength in our relationship. So, number of siblings and number of children. This is data I actually collected in a former psych stats class. And you can see that as the number of siblings increases, you kind of see inconsistent increase and decrease in number of children, right? Like, oh, here it's starting to look good, right? Small and small numbers. But then it gets a little bit larger, and these people still have one sibling. And then, whoa, this person had 3 children and they only had one sibling. Whereas this person had 4 siblings and only had one child. You can just kind of see it's inconsistent. The picture becomes more clear when you plot it out in a scatter plot, right? It's kind of spread out. Now, one way that you can think about figuring out, because it's important for you to be able to look at a scatter plot and make a prediction about what you think the correlation coefficient will be once it's computed. So if you have a situation where your data comes pretty close to a straight line, even if it was kind of scattered around this straight line, that would be a strong relationship. If you had a situation where your data looks like this, you can kind of visualize, all right, I can see that my data points are pretty spread out, but I can tell what the direction is, right? I can tell that this is positive. If I draw a circle around this data, it's going in an upward direction. So if you have a situation where your data points are scattered, but you can still discern the direction of the relationship, it's probably a good sign that you have a moderate strength. I think the textbook says if you draw a circle around the data, it looks like a football. That's probably a moderate strength. That's another way to think about it. And if you look at the correlation coefficient for this, it's 0.283, pretty close to 0.30. We're calling that moderate, right? Whereas this one is a 1, that's above 0.70, very strong relationship. In fact, this one's perfect because it's 1. Perfect relationship. All right. So if you were asked to describe why you think, what strength do you think the relationship is, and how do you know based on the scatter plot, you could say, in this example, I think that this is moderate strength because although the data points are scattered, I can see that there's an upward slope. I can tell that the direction is positive. Or if I drew a circle around this data point, it would be kind of a football shape. Whereas this one, you would say, I think this is a strong relationship because the data comes really close to fitting on a straight line. Well, in this case, it fits exactly on a straight line. For this one, you could say, this looks like a weak relationship because my data points are so scattered that I don't even know what the direction of the relationship is. If you calculate the correlation coefficient based on this data, you'll see it's negative. But you can't tell that from the picture. And you can also see here, it's a very small correlation coefficient, right? 0.085 is even below this 0.10, so we'd say it's a weak relationship. And if you look at the data, you can see that it's placed in order of who got the lowest to the highest grade on anatomy and physiology. And then when you look at Y, you don't see really any pattern related to X. So this is some data based on a study that showed that among nursing students, their grade in anatomy and physiology pretty much has nothing to do with how well they do on clinical exams within the nursing field. So there's this thing that's called the objective structured clinical examination, where they have nurses or prospective nurses go to different stations and perform different tasks, and they grade them on how well they perform the tasks. And again, that doesn't appear to have a relationship with your grade in anatomy and physiology, which is a really important class in most medical programs. So we see this data, we see the weak correlation, right? Not a consistent pattern, and the data points are spread out all over the place. So the steps of a hypothesis test with correlation. So step one is still stating your hypothesis. And in symbols, we have all the different possibilities that you could have. And with this little, and so we kind of got away from one or two tailed tests when we were doing ANOVA, which I'm sure everybody was very happy about, but now it is back. So I kind of want to talk about that first before we look at the symbols. So if you have a two-tailed test, that means that you are just expecting that there's a significant relationship between the two variables. You're not being specific about the kind of relationship that you're looking for. If you have a one-tailed or test, maybe you're looking for a positive relationship or a negative relationship. So you're being specific about the type of relationship that you're looking for. So, for instance, if I think that those who study more will tend to have higher quiz grades, that should tell you that I'm expecting a positive relationship and we're doing a one-tailed test. If I said that I think those who have more class absences will have lower quiz grades, then you'd know I'm doing a one-tailed test, but it's a negative correlation that I'm expecting. If I just say I think there's a relationship between class absences and quiz grades, but I'm not specific, that's a two-tailed test. So let's break down these symbols. So this little p represents the population correlation. So whenever we state our hypothesis in symbols for all the tests that we've been doing, so for instance, when you're doing a t-test, you would state it in symbols using mu, not m, right? Because we are testing a hypothesis about the population. We don't really care about the sample in of itself. We just care about what that sample tells me about the population. And if you get a significant finding and you reject the null hypothesis, then that tells us that what we saw in our sample is probably happening in our population. So this little p just represents the population correlation. And if it's a two-tailed test, under the null, the correlation in the population would be, pretty much no correlation, right? Zero. There's no relationship in the population. Keep in mind that in our sample, our correlation could be something other than zero, but we could still fail to reject the null because it's not a strong enough relationship for us to expect to see a relationship in the population. And then under the alternative, there's some relationship, right? The correlation coefficient is not equal to zero in the population because there's some relationship. Remember, a correlation coefficient of zero means there's no relationship at all, no consistent pattern across your two variables. If we had a situation where we were expecting a positive relationship, higher values for x tend to correspond to higher values for y, then our null hypothesis, well, let's start with the alternative. I like to start with the alternative when we're doing a one-tailed test because it's like state what you expect in the alternative and then the null is everything else. So if we expect a positive relationship, then in the population, our correlation would be greater than zero, right? If it's positive, it's going to be anything above 1. Above 0, from 0 to 1. Remember, you can't have a correlation that exceeds a value of 1. All right, null, if it's not greater than 0, it's less than or equal to 0. So if we have a one-tailed test, we're expecting a positive relationship. The null would say that in the population, there's either a negative relationship or no relationship at all. Then for the negative one-tailed test, if we're expecting that higher values for x tend to correspond to lower values for y, then under the alternative, we think that the population correlation would be less than 0, right? A negative value. And under the null, if it's not less than 0, it's greater than or equal to 0. So if it's not a negative correlation, it's either a positive correlation in the population or no correlation at all, equal to 0. Now let's look at step 2, determining the critical region. So F was really nice, right, when we did ANOVA, because we didn't have to worry about which tail the critical value represented because any high value was going to be in that critical region. Well, now we're back to one or two tailed tests, and we're also back to making sure that you shade in your critical region and the appropriate side of the distribution if you're doing a one-tailed test. So if you have a one-tailed test and you think you have a negative relationship, then your critical region is going to be on the left side, the extreme left tail of the distribution, less than 0. And 0 is going to be in the middle, like it always has been. If you expect a positive relationship and it's a one-tailed test, then you're going to have a situation where your critical region is on the right side of the distribution, representing the extreme right side, the right tail in the distribution. And then if you have a situation where you have a two-tailed test, you're going to have the two tails on either end of the distribution. So let's talk a little bit about finding our crit, the critical values for the Pearson correlation. So let's go ahead and look at that table and I'll show you what's within it. Look at my happy screensaver. So cute. Or not my screensaver, my desktop. Okay. So here is the Pearson correlation table. And you'll see, just like the t-table, it's nice and friendly. It breaks down whether we're looking at a one or a two-tailed test. So we don't have to split alpha levels here. And we also need to know, so not only do we need to know is a one or two-tailed test, we need to know the alpha level, we need to know the degrees of freedom. And this table is really friendly because it tells you right here how to calculate the degrees of freedom. So as long as you keep in mind that little n, the sample size, represents how many people are in your data, and that when you look at it, let's go back to, don't be counting, oh, I have 1, 2, 3, 4, 5, 6, 7, 8. Don't count how many scores you have. Count how many rows you have, right? Because remember, each person in your data set has 2 scores. So our sample size in this study would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And 19 minus 2 is 17. That would be our degrees of freedom. All right, so let's look at this table again. So n minus 2 is your degrees of freedom. You find it here. And then one or two-tailed test, find your alpha level. So let's say we were doing a one-tailed test with an alpha level of 0.05 and our degrees of freedom was 16. We'd go right here, one-tailed test, 0.05, 16, critical value, 0.400. And if it was a one-tailed test where we're expecting a negative relationship, then that critical value would be negative 0.400. And if we were drawing it out, we would shade in the left side of the graph. If we had a two-tailed hypothesis test with an alpha level of 0.05, degrees of freedom 16, meaning that we have 18 people in the study, right? 18 minus 2 is 16. 0.05, two-tailed test, 16. Right here, critical value would be 0.468. So just like it's always been, when you have a two-tailed test, your critical value is going to be larger. Although the table does it for you, it is essentially splitting that alpha level. So if our alpha level is 0.05, then our calculated R statistic, our correlation coefficient, has to fall in the extreme 5% of the distribution. Well, with a one-tailed test, that whole 5% is in one tail. But with a two-tailed test, we're basically looking in the extreme 0.025% of the distribution on either side, so we have a larger value, right? It's a more extreme value because it's further out in the tail. Just kind of a conceptual side note there. So I just break it down for you, right? Our crit is based on the alpha level, usually either 0.05 or 0.01, one or two-tailed test, and then your degrees of freedom. And I even put a little note here, right? N represents the number of study participants or pairs of scores. So I don't want you to get messed up by counting how many scores are in your data set, because remember, each person has 2 scores, their score on X and their score on Y. Now here are the steps for calculating your correlation coefficient, or R. Now conceptually, the correlation coefficient takes the degree to which X and Y vary together. They're consistent, how consistent they are, how they vary together, or their covariability, and divides it by the variability of each. So the degree to which X and Y vary separately. So again, the relationship between X and Y, you can find the correlation coefficient that tells you about the relationship by taking the degree to which X and Y vary together divided by the degree to which they vary separately. Now, these are the symbols for this. So SP stands for the sum of products, and the sum of products is a measure of covariability, how two variables vary together, how they change consistently from one participant to another. Then you're dividing by, remember, variability is a measure like the sum of squares. We've been seeing the sum of squares a lot. So the denominator is the sum of squares for X, the degree to which X varies, multiplied by the sum of squares Y, the degree to which Y varies, right? The degree to which X and Y vary separately, the variability of each. A measure of variability is the sum of squares. So you're just combining the variability for each variable separately. And you'll multiply those two together, and then you're going to take the square root of that in your denominator. To get the sum of products, it's very similar to finding the sum of squares that you've seen before, right? Look at these sum of squares formulas. You've seen these before. The sum of squares for X, you've seen that many times. The sum of squares for Y, it's basically the formula for the sum of squares that you've always seen. You're just replacing X with Y. So we'll still be squaring each value for X and adding it together, and subtracting it by the sum of x, so all the values added together and then squared. Remember, order of operations, parentheses comes first, and then that'll be divided by the sample size. For y, same thing, just y is being replaced, or x is being replaced with y. And then the sum of products is similar. Instead of taking, x and multiplying it by itself to get sum of x squared, you're taking x and multiplying it by y across all study participants to get this first value. And then you're taking the sum of x, adding all the x's, and multiplying it by the sum of y instead of squaring, taking the sum of x and multiplying it by the sum of x. Now you're taking the sum of x and multiplying it by the sum of y because we're looking at covariability here, right? We're mixing these up. We're putting them together. And then here you still divide by the sample size. I'm going to give you 2 examples in the example problems video using these formulas that'll help you understand that it's really not that different from what you've been doing already. You've been calculating sum of squares. You're just going to be calculating 3 different sum of squares and then putting them in this formula here. So then step 4. So this is when you'll make a decision and you'll state your conclusion. So that's been the same step 4 that you've been doing for your hypothesis testing all along. And it's really the same rationale that you've been using. If what you calculate in step 3 falls into the critical region from step 2, you're good to go. You can reject the null, celebrate, and say that the relationship is probably significant. So if the observed or calculated R from step 3 falls in the critical region, reject the null, correlation is significant. So what that means is that the relationship between x and y, the 2 variables in your study, is probably not due to chance, and you would expect to see that relationship in the population. If you have a situation where your correlation coefficient does not fall in the critical region, then you would fail to reject the null hypothesis, and you would state that the correlation is probably not significant. So the relationship, any consistent pattern that you saw in your data, is probably due to chance, and you would not expect to see that relationship in the population. Now, some guidelines for writing your conclusion in step 4, because you not only want to make your decision, reject the null or fail to reject the null, but you want to state your conclusion. And your conclusion should mention the independent variable and the dependent variable from your study, if the correlation is significant, and if the test is one-tailed test, then you should mention that, I have a significant positive relationship or a significant negative relationship, depending on the context of your study. Okay, now let's get into why correlation is not perfect. Sometimes it's the only type of data that we have access to, is the kind of data that we can do a correlation analysis with. I mean, a lot of times in my experience as an IO psychologist, I can't go into the workplace and start manipulating things. Right? Employers are never going to give me, like, for instance, I study sexual harassment. I can't go in and go, okay, this group gets sexual harassment and this group doesn't, and let's look at differences. It's not okay to do that. It's not ethical. Employers aren't going to let you do it. So oftentimes, correlational data is the only data we can get our hands on, right? And usually it's survey-based data. Usually I could just go into a company and I can say, how often have you been sexually harassed? And then compare that to other measures like performance or work stress or psychological health or things like that. It's correlational data. There's no causation involved. But if you have a culmination of studies that show similar relationships, we can start to be more confident that maybe something is actually going on there. So just kind of putting that out there. A lot of research is correlational because it's a necessity. It's the only type of research that we can ethically do. So most often, correlational studies are not true experiments. Again, they don't involve the manipulation of conditions or control over other factors which may influence the observed relationship between 2 variables. Correlational studies are simply aimed at describing the relationship between 2 naturally occurring variables. Again, typically through self-report surveys. So because correlational studies are not a true experiment, we cannot say that there's causation, right? Remember the true experiment. You can review that lecture where we had to have manipulation, control, and randomization. Those 3 conditions have to be met or we can't make causal inference based on studies. So a significant correlation only tells you that the 2 variables are related, not which variables cause which, or even if there's a cause-effect relationship at all. So in this lecture, I'm going to cover the 4 most problematic aspects of correlation that will help you understand why observing a significant relationship between 2 things does not mean that one causes the other. So the first is independent variable and dependent variable confusion. And I've already kind of mentioned that it can be unclear which variable that you're looking at is the independent variable and which is the dependent variable. So what I'm really saying is that the direction of causality, if there is any causality, that direction is unclear. We don't know which came first. So if we look at these examples and the way that you draw a correlational relationship when you're plotting it out in a model is you put this little double-headed arrow here. And that double-headed arrow indicates that we don't really know which one came first, right? They're just related. We don't have, oh, this leads to this, right? A one-headed arrow, or this leads to this. We have that double-headed arrow there. So if we look at let's say we see that there is a strong negative relationship between overtime hours and marital satisfaction. Well, we could say that if a spouse works more overtime hours, that leads to less satisfaction in their marriage because they're spending less time together. I want you to kind of maybe pause this video and think about other ways that that relationship could play out. So go ahead and pause it and think about how we could see a strong relationship here, and it's not due to the fact that more overtime hours lead to less marital satisfaction. Okay, so let's go ahead and stick with thinking that overtime hours is the independent variable, right? Maybe we see a positive relationship. Maybe those who work more overtime hours have more marital satisfaction. Maybe they're making more money, so they're more satisfied in their marriage because they can do more fun things when they do have time together. Or maybe absence makes the heart grow fonder. They're spending less time with each other. They're working overtime, so they're more satisfied in their marriage. Or maybe marital satisfaction is the independent variable. Let's get real negative and say that maybe you are dissatisfied with your marriage, so you work more overtime hours. So there's a negative relationship, but it's not because more overtime hours leads to less marital satisfaction. It's because less marital satisfaction leads to staying at work. You're not trying to come home and be with that spouse that you're not very fond of. So that's IV-DV confusion. Another example would be job satisfaction and performance. So there's a lot of research suggesting that job satisfaction leads to increased levels of performance, but then there's also research that suggests that maybe it's an inverse relationship. Or not really, yeah, inverse. So maybe it's that those, and we always usually see a positive relationship here. So it could be that those who work or have more job satisfaction have higher performance. They're happy, so they're performing well. Or maybe those who perform well have more job satisfaction, right? You're good at your job, so you're feeling good about it. Or maybe you're not so good at your job, so you're not feeling so satisfied. You feel dumb at work. You feel like you're not doing the right thing. You feel confused. You have less confidence. So that's just an example of how it may not always be clear which variable is coming first in that observed relationship. Now let's look at restriction of range. So remember, a sample is less variable than the population is drawn from. Remember way back in the day when we talked about measuring standard deviation or variance? When you're looking at the sample, we take n-1 in the denominator there to bump up the overall value of that measure of variability, because we know that the sample underestimates how variable scores are in the population, how spread out scores are in the population. So because a sample tends to be less variable than the population, it doesn't represent the full range of scores in the population, it's possible to obtain a sample that in fact does not represent the full range of possible scores for X and Y in the population. And when you compute a correlation from scores that do not represent the full range of possible values, the correlation can be very misleading. So if you're only looking at relationships in a limited range of scores, the correlation may be pushed closer to zero. So here's an example of that. You saw this when we talked about weak strength, right? Grades on the anatomy and physiology class and how those are related to the percentage of passing stations on the objective structured clinical examination. And we identified that was a weak relationship. And not only it's weak, right, because this value is close to 0.10, but it's also negative, right? Negative value. So they're changing in opposite directions, but not very consistently. So this is a weak relationship. Well, this could be due to restriction of range. Because if you think about it, those who do really, really poorly on anatomy and physiology, because that's a really important class that you take, maybe they did horrible in anatomy and physiology and they changed majors. They're like, I can't hack this medical stuff. So they never even got to the point where they were doing the OSCE. So we don't have the data for those people who did poorly on anatomy and physiology because they never got to this point. So what if we did have the full range of data? What if we took those people who failed out, got a bad grade in anatomy and physiology, and gave them the OSCE exam to see how well that they did? Well, then, if we have the data for these people who did poorly, we start to see a strong relationship. If we drew a circle around this data, it would be very upward direction, and it would be more linear. We'd have a more narrow circle if we drew a circle around our data set. As opposed to here, if we draw a circle around these data points, it's a big, huge circle, right? It's not very narrow. The data is just scattered all over the place. So this is an example where you don't have the full range of scores in the population. You don't have this. You're just left with this, and the overall relationship looks weaker than it is in reality. This is also something that you see in industrial organizational psychology. I'm an IO psychologist, so I like to bring up, work-related examples. So let's say that we're looking at the relationship between a selection test and performance. Well, typically, we aren't going to hire people who do poorly on the selection test, so we wouldn't have those low scores on the selection test, so we wouldn't be able to compare the performance for people who scored low on the selection test, right? So we'd have restriction of range. We'd only be left with people who scored high enough on the selection test to get hired. So we would only have performance data from people who scored well on the selection test, and we would probably underestimate how well that selection test predicts performance. Again, we wouldn't have those values in the low end, just like we have here. Restriction of range. Another reason why correlation does not equal causation. All right, now let's look at outliers. So outliers are just one or two extreme scores that can drastically alter the observed correlation coefficient between two variables. Remember how the mean can be biased by an outlier? So remember when we have extreme values in our data set, or when we have skewed distributions, we use the median because the median is not really impacted by extreme values. Same thing happens with outliers and correlation. So if you have any outliers in your data, the correlation can appear to be stronger than it really is just because you have a couple of extreme values. So there's a couple of ways to deal with outliers in research. If you're looking at your data and you see, whoa, there's a couple of people in my data set that have crazy extreme scores that are nothing like the rest, you can remove those outliers. Just make sure that if you're writing up a research report, that you mention that you removed outliers. Or you can conduct the analysis with and without the outliers and report both results. So here's an example where outliers can impact your data. So remember this moderate relationship between the number of siblings and the number of children. Relationship around 0.283. It's positive. You can kind of remember moderate strength. You can kind of see it's positive, but the data points are still pretty spread out. What if we added one more person to our data set and they had 10 siblings growing up and had 10 children? So whereas before, if we drew a circle around this data set, it would be kind of a wide-ish circle, right? It'd be kind of football shaped, so we have a moderate strength. Now if we drew a circle around this data set, that circle becomes more narrow. It appears to be stronger, more linear, and it's certainly positive, right? So this one person added to our data set made our correlation coefficient go from moderate, 0.283, to strong, 0.713, very strong, just by adding that one person. That is drastic and kind of scary because think about it. If you're a researcher and you're desperate to publish results, it's really hard to publish findings if they aren't significant. So you may see an outlier in your data, get this beautiful, strong, significant correlation, and really never even be inclined to report the fact that you had an outlier in your data and that's why it was strong, when in fact, the majority of data suggests it's a moderate relationship. So researchers can be tricky that way. They're desperate to publish. They want beautiful, significant findings. They want to support their hypotheses. And they'll just say, there's an outlier, but I'm not going to talk about that because I love the results that it gave me. So again, I'm trying to make you a critical consumer of research and hopefully make you a more ethical researcher where you probably should have maybe done the analysis both ways, like reported both this and said, hey, there's this outlier here that's making this relationship strong. Yeah, they still count, but they don't represent the vast majority of scores. Now let's talk about partial correlations. So you can have a situation where there is a third variable that's related to the two variables that you're looking at in your correlation. And it's really not the fact that those two variables are related, it's the fact that those two variables are related to a third variable. And I'm going to show you examples of this. So again, a significant correlation just tells you that two variables are related, but it doesn't tell you anything about causal effects. And sometimes, for instance, you see a relationship between two variables and it doesn't really make sense. And maybe it's because these two things are related to a third variable and aren't actually related to one another. So for instance, this is a classic example where you look at ice cream sales and crime rate and you see this strong positive correlation. So you may be inclined, if you're not a wise consumer of research, to say, oh my goodness, ice cream sales increase crime rate. So maybe people have a sugar buzz, they're eating all this ice cream, and they go out and they commit some crimes. Or maybe it goes the other way around, right? Maybe after committing all these crimes, they've got a hankering for ice cream. Probably not, right? Maybe there's a third variable that both of these things are related to that have an impact on this observed relationship. And we'll look at that here in a second. Here's a less silly example. So there's a lot of research out there that suggests that students who take more credit hours each semester have a higher likelihood of graduating college, actually finishing their degree. And it's a very strong positive relationship. And on the surface, that appears to make sense. But there are several other variables that are related to how many credit hours you can take each semester and how likely you are to finish college that inflate or strengthen this observed relationship. And we'll look at that after we look at silly ice cream sales and crime rate. So I'm only going to go over the interpretation of partial correlations. In this lecture, I'm not going to go over how to actually calculate this partial correlation that you see here. So you've probably heard this example before. Temperature is the reason that you see a positive relationship between ice cream sales and crime rate, right? There's a strong positive relationship between ice cream sales and crime rate. As the temperature increases, ice cream sales tend to increase, and a strong positive relationship between temperature and crime rate. As the temperature increases, crime rate tends to increase as well. And so if we calculate our partial correlation coefficient, this is a magical tool. This is saying, what is the relationship between x and y after we control for z, after we control for that other variable that we think x and y are both related to. And if you conduct the partial correlation analysis, you see that after you control for the fact that ice cream sales and crime rate are both related to temperature, that correlation goes from a 0.85, right? That's the original correlation between crime rate and ice cream sales, to a negative 0.035. So it goes from strong and positive to weak and negative. And I wrote out the description of how to interpret this here because students do have a difficult time figuring out how to parse out these effects. So this is essentially saying that once you control for temperature, there's really no relationship between ice cream sales and crime rate. And you know that because you compare the original correlation between x and y, right? This strong positive value to what the correlation becomes after you control for the fact that both x and y are related to z. And it becomes very weak and actually changes direction. So this is drastic. We can pretty confidently say that the only reason we see a strong positive relationship here between ice cream sales and crime rate is because both are related to temperature. So here's a funny cartoon. So man, it's hot. I'd kill for an ice cream cone, right? So this is suggesting that you want ice cream, so you're going to commit a crime to get it, and that's why we see that strong positive relationship. But in reality, it's sweltering hot, and as it gets hotter, crime rate goes up, and ice cream sales go up as well. So you see a nice little scatter plot there. I think that's a perfect illustration of that strange, strong positive relationship between crime rate and ice cream sales. Here's another example based on number of credit hours and college completion. So maybe part of the reason that we see this strong positive relationship between how many credit hours you take each semester and how likely you are to complete college, because both are related to how many hours you spend at work per week. So if you're working a lot, you're probably not able to take as many credit hours, right? You're working full time. You don't have time to take a full course load. And if you're working a lot, then maybe it's that obligation of work that gets in the way of you completing college. Or maybe you're working a lot and you get promoted because you're working so hard and you're no longer as motivated to get your degree because you're already in a position that you like and the whole reason you were in college was to get a better job. Several reasons why average hours spent at work per week would be related to both number of credit hours and college completion. So we see strong positive relationships across the board. And when you do the partial correlation coefficient, looking at the relationship between number of credit hours each semester and college completion, controlling for the fact that both are related to average hours spent at work per week, you still see, a pretty strong correlation. So what that tells me, it got weaker, right? So part of the reason that we see this strong positive relationship is because both number of credit hours each semester and college completion are related to average hours spent at work per week. But that's not the whole reason that we see that relationship there. So you can see that description of how to interpret those results written down here to help you understand what you can think about when you're looking at partial correlations compared to the original correlation. So again, you're comparing the original correlation between x and y to the correlation between x and y after controlling for z. So after watching this lecture, I hope that you feel like a wiser consumer of research. You can be more critical when somebody tries to make causal inference based on correlational data, and that you are prepared to do some example problems with correlation.